All right, so let's solve this example problem from the ULB textbook. This is a transformer example. Of course, our transformer is an ideal transformer. We can see that it's given. It's characterized by this turns ratio 1 to 4, so it is a step-up transformer. Okay, and we know that means if I write this as V1 and this is V2, and I write this as I1 and this is I2, right? I know that means that I2 is equal to 1/4 of I1. And I also know that V2 is 4 times V1, right? Those are my current voltage relationships there for my turns ratio of 1 to 4 across this step-up transformer. Again, it's called a step-up transformer because it's stepping up the voltage. Typically, I'll just say transformer. Typically, we don't say step-up transformer based on anything other than the voltage. We're talking about this turns ratio is always characterizing the voltage step-up or the voltage step-down of the transformer, and then the current is just the opposite. We're very rarely, I guess there are things called current transformers, which have different specs, but we're talking about voltage transformers here. So the step-up transformer is referring to the fact that the voltage is being stepped up from primary to secondary. Okay, so just wanted to clear that up. So let's write an equation here for V out, because this problem basically asks us to find V out. That's what we're being asked to do here. So we know that this current is I2, so we can write that V out is equal to I2 times 32 kilo ohms, basically. It's just the voltage dropped across that 32 kilo ohms. So I'll write that V out is equal to I2 times 32 kilo ohms. Well, we also have an expression already for I2 in terms of I1. So we could write equivalently that that's equal to 0.25 times I1 times 32 kilo ohms. And so then that gives me V out is equal to I1 times 8 kilo ohms. Okay, so we've got an expression for V out with V out and I1. And there's another expression that we could write. We know this voltage here, V2, is equal to V out. Let me write that. You can tell that they're the same voltage, right? We're talking about the voltage from the dotted terminal to the undotted terminal, and that's the same two nodes that V out is connected to, right? So V out and V2 are equal to each other. And we know that V2, I'll just write V out right here. We know that V2 is 4 times V1. So what we really need is an expression for V1. And we can get that because we know that V1 is equal to 12 angle 0 minus the voltage dropped across that 1K resistor, which is just going to be I1 times 1 kilo ohm, right? I hope you would agree with me that the voltage dropped across this resistor is going to be I1 times 1 kilo ohm. Okay, so then V2 or V out is just 4 times that, right? It's 4 times this voltage, so it's going to be 12 angle 0 minus I1 times 1K multiplied by 4. All right? And so now we have an expression here for V out and I1, and we have an expression here for V out and I1, and we can solve this system of equations to determine our V out value. Okay, so let's solve this one for I1. We can say that I1 is equal to V out divided by 8 kilo ohms. And so I can plug that in here. V out is equal to 12 angle 0 volts. I haven't been writing volts this whole time. Minus V out times 1 kilo ohm over 8 kilo ohms. And then that whole thing is multiplied by 4. So I can say that this is equal to 48 angle 0 minus 0.5 times V out. I can add the 0.5 V out to the original V out, so I get 1.5 V out is equal to 48 angle 0 volts. And lastly, I can say that V out is equal to 48 angle 0 divided by 1.5, or basically multiplied by 2/3. And so we get that V out is going to be 32 angle 0 volts, okay? And so we basically just set up a bunch of equations for this transformer that we know are valid. We started with the current and voltage equations, and then we started using Ohm's law at V out, Ohm's law here, and then we started plugging in and substituting until we got our value for V out here, which is 32 angle 0. I'm going to build this circuit in LT-Spice in one of the following videos so that we can see that this is the case, and I'm going to teach you how to implement an obviously there's no inductances here, there's no mutual inductance, there's no coupling, so it's kind of interesting. When you have an ideal transformer, there's a unique way that we can implement that in LT-Spice. So I'm going to show you guys how to do that in one of the coming videos. But before I do that, I want to basically resolve this problem on the next slide using a different method, because it just so happens that I think I talked about how we can transform voltages and currents through a transformer. We can also transform impedances across a transformer, and that's also really powerful. So in the next video, I'm going to show us how we can, or show you guys how we can basically transform this 1 kilo ohm impedance over across the transformer, and then transform the voltage across the transformer as well, and then solve for V out using that equivalent circuit once we've transformed these elements over to the other side. Okay, so that's also really interesting, and we're basically just going to resolve this same problem. We should arrive at this exact same result in the next video, but using a different method. All right, so I'll end this video here, and we'll see you guys in the next video.